Hello, my name is Mike Avery from Cadence Design Systems, and in this video I'm going to talk about some of the practical uses of the mod operator in VHDL. First thing to note about the VHDL mod operator is it's not like the mod operator you find in other languages like, for example, System Verilog or C++. The purpose of this video is to actually describe what we can use the mod for in practice, not how it works. I'll show you a link to a video later on which shows how mod works and why, but for the moment what we'll do is just look at the Language Reference Manual definition of mod, and to all intents and purposes it doesn't serve as a very intuitive explanation. So if we were to look at the latest Language Reference Manual for VHDL, which is this standard shown here, 1076, the current version at time of making this video is 2008. That's the latest version. Current date is November 2018. So if we were to go in this manual and look in expressions and in operators, we will find all the VHDL operators defined. The ones we're looking for is the arithmetic operators, and in particular the what's known as multiplying operators. In most maths descriptions, division does not exist. It's everything's a multiplier if it's not an addition. And so we see here a list in this table of the operators, so multiplication and the inverse of that, which is named a division, and rem, which behaves as a normal integer remainder, which is very familiar to us from any maths or any other language. Now this rem operator behaves much like the mod operators in other languages. So rem in VHDL behaves like mod in C++, for example. So that leaves the question, what does mod do then? Well, here's a description of what mod does. So this is where this description starts here. So it's telling us that if we have an operation a mod b, the result has the sign of b and an absolute value, a magnitude, which is less than b. And for some integer value n, this should satisfy this relationship shown here. Okay, so what I'll do is I'll show you this on a slide, and we're going to reorganize the formula. There's just a repetition of what the Language Reference Manual said. Here's a formula which we can, just to make things easier, convert to this. So all we've done here is take the b multiplied by n term and move this to the left hand side of the equals operator by subtracting it, and therefore this a minus b times n gives us the value of result of the mod operation. So an interesting observation, and we're not going to go into detail, as I said before, about what mod does and how it works here, but if the sign of a or b are the same, i.e. they're both positive or they're both negative, then they actually do the same thing. The result will always be the same. So if we have something that we're familiar with, like 8 rem plus 5 would leave us a result of plus 3. Just imagining that we had the rem operator here and not the mod operator for a moment, just to explain this. 8 divided by 5, 5 divides into 8 once, and we have 3 left over, so that's where the result plus 3 goes for. And we've said from the statement above that a rem b equals a mod b if the sign of a and b are the same, which they are. In this case, they're both positive. So we already know this. We already know that a mod 5 equals plus 3 by deduction. And from this box up here, we reorganize this equation from the LRM into this expression here. So all we can do here is we plug the numbers a and b that we know, a being 8, b being 5, into this equation here, and we see we end up with this 8 minus, and in brackets 5 times n equals plus 3. Now n is not the result of the operation. Okay, so when you see the term n here, this is just some integer. Remember that mod and rem are describing integer arithmetic, so n is an integer. It is not the result of the operation, other than by coincidence, as we'll see in a moment. So what we'd have to do then is choose a value for n, and there was only one value that will satisfy these equalities here, these equations. And then if we find one integer which satisfies that equation, we know that the plus 3 is the right answer, which we've already arrived at by deduction. Okay, so what values could we choose for n then? Okay, so let's choose a starting value n equals 0, for example. Let's see if this works. Well, 8 minus 5 times 0 is obviously going to be a result of 8, which violates this statement up here. The absolute value is not less than the value of b. So remember, b is plus 5, so it can't be the value 0. What about the value 2? Well, if we add the value 2 for n, this means we have 8 minus 5 times 2, which is 8 minus 10, which will end up with a negative result, negative 2. And this violates this statement. The sign of b has to be followed in the result. So it wouldn't be, would it? If the result was minus 2, then that is not following the sign of b. b is plus 5. If we have the value 1 here, okay, so 8 minus 5 times 1 is 8 minus 5 equals 3. So that number we've chosen here, the integer plus 1, is the only integer that will satisfy those equations. Therefore, this confirms to us that the result of a mod 5 is plus 3. Okay, so that's all very well, but what about the circumstances under which that mod does not behave like rem, i.e. the sign of A and the sign of B are different. One's positive, one's negative. So here's a known result. So this known result comes from the other video that I'll show you a link to later, which describes how the mod operator works and how you can actually do mod operators in your head. So I'd advise you to go and watch that video. It's fairly lengthy, but there's not a lot left to explain about mod that isn't covered in that video. How do we do this? We go through the same sort of process. Let's just choose a value for n, which will satisfy this. So again, we could just guess, couldn't we? We could just say 8 minus 5 times 0. What result does that give us? That gives us 8. Clearly, the sign of B is negative and the result of 8 is positive, and it also violates this. The result has to have a magnitude less than B. What about choosing a value of +1? Well, that will leave us 8 minus 5 multiplied by +1, which will leave us 13. That's our result, 13. 13 larger in magnitude than B, therefore that can't be right either. Let's choose a negative value, -1. Okay, so this gives us 8 minus 5 times -1. So -5 times -1 is going to be +5. This gives a result of 3, which leaves us with the sign not being the correct value. We're expecting a negative value here. Finally, guessing a number for n leads us to the correct result. Let's choose n minus 2. We then have 8 minus -5 multiplied by -2, so 8 minus 10. So that leaves a result of -2. So that has to be the correct answer because it's the only integer which will suit all the statements in this blue box here. Okay, so now we understand that mod is not the same in VHDL as it is in other languages, and rem in VHDL is not the same as mod in VHDL. What does this leave us that we can do usefully with mod operator? So many examples you see are in cookbooks and so on. You'll see exactly this example, i.e. it looks like it's the only use mod ever has. So what it allows us to do is reset a count at a certain value. So if we say mod 16, what we've described is a counter here in this case, which ranges from 0 to 15. So it'll count from 0 to 15 and then loop back to 0 again. We can't get up to the number 16. Okay, so we just keep looping 0 to 15, and of course we can change this number at any time. The thing on the right hand side of the mod operator, we could change that at any time. However, what we need to be aware of is if you want to synthesize this, the right hand side of mod has to either be a power of 2 or a constant if you wish to synthesize that. So this is, maybe used in test benches, for example. So lots of places, require mod, like in a mathematical construct called fields or rings. So what this mod operator does is, in effect, it allows us to describe things less verbosely. Instead of, writing out this entire statement, which you would do if you wanted to actually synthesize this reliably, if you wanted to change the value at which the counter reset, you'd have to type out more things, and it's less easy to follow than this statement above. So maybe a better example, which you don't see very often, is if you want to control indexing of items in an array. Remember, in VHDL you can have arrays to any arbitrary dimension, so this might be very useful, not just in design but also in test benches. So let's say we've got some data streams coming in and we want to put that data into 4 different sets, starting at 0. And we don't want the ordering to be affected by whether the index to this array is negative or positive. So in VHDL, remember that an index to an array can be anything. It doesn't need to be an integer, it doesn't need to be positive. It can be anything you like, associative arrays, for example. And what we're going to use in this case is we're going to use mod to make sure we order this array in the way we wish. So if we wanted to pass something into a set with a negative index, we can just merely state m, which set I put things into, is the current index mod 4. Okay, so if I were to plot this out from a negative index value to a positive index value, what we can see, this pattern here, 3, 0, 1, 2, 3, this repeats consistently through the boundary of going from negative to positive. So that might be a useful thing to do. So the next question is, why would I want a negative index then? Well, it might be, you've got some constructs like, as we talked before, about fields and so on, and rings. It may be that you wish the index to represent a power of 2. So for example, it's like a fixed point kind of thing here. This index -1 might represent 2 to the -1, i.e. 1/2. This index 2 might represent 2 to the power of 2, i.e. 4. So there may be loads of reasons we want to do this and maintain this data ordering still. If we use rem, and languages like C++, for example, don't have an equivalent of this VHDL mod operator. So if you're doing this in C++ or System Verilog, the only thing you could do is use rem. And what you find if you did the same thing here is to generate which set of these things going into, then you'll find that the result is mirrored around this boundary between positive and negative and reflected. So here, for the value 0, the values immediately to the left is the inverse, i.e. negative value, the same as this. And if you go one more element to the left, -2, is a mirror of +2. And notice also these things do not go in the same order all the way through. You can also see that the sets to which we're putting these things in, these notional sets, these numbers do not follow the same order either side of this boundary. So like if we were to start from this position, for example here, -7, we're going to set 3 once, twice, and then not again. There's 2 times into set 1, 2 times into set 2 before we put another item into set 3, if we were to use the rem operator and discard the sign. Okay, so there's a reason mod exists. It's not in the language reference manual for fun. Having said that, a lot of people don't use VHDL for creating kind of complex test benches these days, but historically people did, and if you're a company who only uses VHDL, then that's your only alternative, so it might be worth investigating how this might apply to your kind of data structures. Thanks for listening. I hope you found that useful. I mentioned that there was a video explaining exactly what the mod operator does and how to work the answer out in your head. You can find this in 2 ways. One is just go to Google, type mod operator VHDL, and this is the video here. If I just click that, this lands on a Cadence YouTube channel, so you'll see this video. Another way is support.cadence.com, so just type in your browser support.cadence.com. You will need a login for this. You need to register, and you have to register with an email address that's a proper company. You can't put Gmail or anything similar in there. And when this page comes up, just say VHDL mod operator, and then you'll see there's a video for this. So you find these such videos to help you with languages and also tool-specific things, and a lot of them are in these kind of tab viewers where there's lots of different related subjects down the right hand side here. So how to save lots of recompilation time using VHDL, why you shouldn't name a library, work, and so on. Okay, so try those out. My name's and again, thank you once again for listening. Goodbye.